Hey, hello. So my name is Nobuaki Kubo from Tokyo University of Marine Science and Technology. So I belong to the GNSS laboratory. I'm a professor at this laboratory. Today, I would like to introduce our laboratory briefly. Yes. The goal of our laboratory, so everything related to GNSS is our scope. Because the use of GNSS has been changed according to the varieties of requests from society. So we try to adapt these kinds of requests from society. So this is my just predictions of the near future of GNSS. So currently, centimeter accuracy is becoming popular in the world because the low cost, very good GNSS receivers, dual frequency GNSS receivers is available. So as a human nature, we want to know where we are. This is a very basic, our human natures. And then, so we need a reliable position. So is your position reliable? So we have been asked for many times recently because the the autonomous car requires the reliable positions. And after that, if the position is not reliable, we have to inform it. So this is the definitions of integrity. So we need high integrities, not only for aircraft, but also for other moving platforms like ship and car. Yeah. So even consumer car requires this integrity. Yes. If the position is not reliable, we have to inform it. Okay, what is the next GNSS? Actually, I have no idea. GNSS is already very important infrastructures, not only in Japan, but also in the world. So everyone knows GPS and GNSS. But we need to clarify where we can use GNSS and where we cannot use GNSS. Yes. So there is, yeah, definitely there is limitations of GNSS because, in the under the water and in the tunnel, it is impossible to receive the radio wave from the satellite. And currently, so low Earth orbit satellite is becoming very popular. So actually, the GNSS is developed by country, the government. But currently, so the even company launch the rocket into the space, and for example, SpaceX, they plan to launch a lot of LEO satellites in the space. So maybe we have to think about LEO GNSS for the commercial use. It's not government use. Even government use, maybe LEO can be used. And integration with other sensors. So for example, IMU and speed sensors have been used with GNSS for many years. So there are many research and developments by many researchers in terms of integration GNSS with IMU and speed sensor. But recently, as you know, the radar and the camera are also available. So we have to, change from not only IMU, but also the other sensors like LiDAR and the camera is available because autonomous cars already uses this kind of, sensors, LiDAR, radar, and camera. So we can integrate GNSS with these, new other sensors. So our laboratory, so we have one emeritus professor, Yasuda Sensei. Yasuda Sensei was my boss, and me, and one guest researcher, Mr. Takasu, who is a developer of RTK-lib. So yeah, RTK is very popular, not only in Japan, but also in the world. So we currently are modifying RTK-lib at our laboratory. And one or two postdoc normally from overseas or also in the Japan. So currently we have 3 PhD candidates and 6 master course students and 6 bachelor course students and 1 or 2 administrative assistants. So these are the members of our laboratory. The locations. So you can search our positions, you know, this latitude and longitude. Yeah, so you can find our building in very close to Tokyo stations. So if you need GNSS data, please email me because we have operated 2 base stations for many years. Yeah, you can get the observation data of Network R9 as well as F9P and also the TOPCon receivers we have used for these base stations. So our laboratory is located in very convenient locations. So only 15 minutes by not train, not car, by bicycle to Tokyo Station. And probably approximately 40 minutes by train to Haneda Airport and 1 hour by train to Narita Airport. This is so very convenient locations from overseas and also even in Japan. Yeah, so actually we have several training ships, but our faculty, so the Faculty of Marine Technology, we have one training ship, Shiojimaru. So the left picture shows the new Shiojimaru. So this new Shiojimaru was built this year. So for the test on the sea using GNSS, we can use this training ship. And the light picture showed the Meijimaru. So this is important. This is actually an important cultural property in Japan because Emperor Meiji was on this ship. So currently, this Meijimaru was on our campus. So we have 2 campuses. 2 campuses in Shinagawa and also in Echujima. Yeah. Okay, so I move on to the research topics. So I chose the 5 research topics. Navigation in GNSS challenging environments and GNSS and other sensors, precise GNSS positioning, and receiver design and signal processing, and alternate radio navigation. So I will briefly introduce our research topics. Okay, so the first one is navigation in GNSS challenging environments. So as you might know, we have used fisheye camera and also the precise 3D building model and also Google Earth. So yeah, these are already maybe conventional methods in GNSS challenged environments because if we use fisheye camera view, yeah, we can detect the line of sight signals against non-line of sight signals. And we have evaluated RTK improvement by using this kind of fisheye camera and also the precise 3D building model. And nowadays, so I collaborated with Suzuki Sensei in Chiba Institute of Technology. So Google Earth is also available in terms of NROS, non-line of sight signal, and line of sight signal detections. And in my view, maybe we can use this 3D building model because the government provides a free 3D building model in Japan. So this is amazing. And we have currently evaluated this, free 3D building model for GNSS. And it seems to be, it can be used for the GNSS prediction in everywhere. Because once we set 3D building model in PC, and we just set, GNSS almanac satellite positions, we can predict the RTK performance, where we can use RTK or where we cannot use RTK. So this is maybe important in the near future. So the second is GNSS and other sensors. So we have evaluated GNSS and low-cost IMU and foil speed sensors. So these IMU and foil speed sensors is very useful to improve the accuracy as well as availability in, especially in urban areas. So in urban areas, we cannot get centimeter accuracy easily. But if you have IMU sensors and foil speed sensors with GNSS, so it seems to be, in our laboratory, so even in dense urban area, in like Tokyo Station, near the Tokyo Station and near the Shinjuku Station, is probably maximum horizontal errors will be kind of 1.3 or 1.5 meters. So this is the, current our test results in dense urban areas. And also, if you have pressure sensors, you can use barometers, because the barometers, barometer variations is very precise. This figure shows the RTK ellipsoidal height and barometer derived height. It seems to be, it's very good compared with general differential GNSS, should-range-based differential GNSS and should-range-based single point positioning. It's huge. 100 meters, over 100 meters is many happens in dense urban areas. You can switch from the should-range-based position into the barometers in terms of ellipsoidal height. And currently, maybe 2 years ago, we have started to use LiDAR with GNSS. So this is an ongoing research project for the young researchers. Next is precise GNSS positioning. As you know, in open sky area, there is no research topics for researchers, because currently, even commercial company provides RTK collection service in Japan, in everywhere. And also QGIS broadcast, CLAS, centimeter level augmentation system, and also the PPP, precise orbit and precise clock, are already available in Japan. So which means in open sky area, there is no research topics for our researchers. But if you look at like this, it's very difficult situations like, on the wall. So this is the view of the fisheye view. It's very limited. The fish, it's very limited. The sky view for GNSS. So even in this case, the sum of commercial construction manufacturers try to get to centimeter level accuracy, and we have collaborated with these companies, and currently, so this is the blue positions we were obtained by our proposal method, and this figure shows the in this here. So we just moved an antenna nearby the wall, and even in the nearby the wall, so we can get centimeter level accuracy of this antenna. So this kind of difficult situations, precise GNSS positioning is now our target. So next is also precise GNSS positioning. So as you might know, so QGIS has yeah, we have already have 4 QGIS satellites now, and 2023, the 3 more QGIS will be launched, and in total 7 satellites are available. So in 2024 and 2027, probably we can use the wide area ionospheric collections in, specified countries, not only Japan, but also the Oceania and Asian countries. So for to achieve the kind of PPP RTK, so we have developed the software for PPP RTK. This is a flowchart of our PPP RTK algorithms. So actually, the postdoc from overseas developed this software, but now we are modifying this software to improve the performance. So the left video shows just one example of this our PPP RTK. Yeah, here is our university, so TAMSAT, Tokyo University of Marine Science and Technology, and we chose the 8 base stations, maybe 60 and 50 kilometers, away. And using these base stations, firstly we have done the PPP air, and we can generate troposphere and ionosphere very precise, errors in this grid. And after that, we will converge. We will, integrate the precise orbit and clock and FGB with these grid generated ionosphere and troposphere errors. And then finally, as a client, we can do the PPP RTK. And this figure shows the test results of at our TAMSAT using these base stations. It seems to be very good. Very good. Maybe it's similar to Shira's. Shira's broadcasted by through the QGIS. But in the near future, yeah, we plan to broadcast this kind of ionosphere collections in the world, in the overseas. So this PPP RTK will be very important software, core softwares for this purpose. Okay. Okay, so the next is receiver design and signal processing. So I actually copied the papers from Professor Siaki and Professor Hampshire. Anyway, yeah. So as you know, the spoofing attack is a very serious issues in GNSS. So, but actually, the mechanism of the spoofing attack is very very easy to understand. So as you can see, these pictures. So here is the truth correlations values, and black plot shows the correlations from the spoofers. And actually, the spoofers, if the spoofers knows the code timing and the Doppler frequency, from true satellite, from true radio, from the GNSS. So you just increase the power of spoofers gradually, and then the peak of the truth is spoofed by the spoofers. And actually, the commercial receivers tracks the spoofed signals, not truth signals. So this is a kind of very basics of the spoofing technique. But if you look at this kind of issues, and if you want to investigate, or if you want to improve the receiver robustness of the receiver, so you have to study about receivers inside of the receivers. So then, and therefore, so we try to use the software GNSS receivers. Yes. If you are interested in this kind of topics, please email me, because not only me, but also the three universities started to this project, open source software receiver project for this kind of, very important research topics. Okay. Yeah, so this is, my student presentations, the spoofing detection on ships. So we have, basically the GNSS actually, transmits the signal from the very different positions, different locations. But, if there is a one spoofer, yeah, the spoofing signal is like this. So from 5 satellites in, real view, real satellite from real satellite, five radio can be received in the ship, on the ship, and a spoofing signal also transmits the 5 signals, and RHCP, and on the sea is this radio is reflected on the sea, and probably the characteristics of the radio is changed from RHCP and LHCP. So the left figure shows the spoofed signal, and the right figure shows the one spoofed cluster and one noise clusters. Yes. So 6 satellites are spoofed. Yes. If you look at the ratio of the RHCP with LHCP, and also RHCP and LHCP, character noise ratio, you can detect our receiver is spoofed or not. So this is just one example of the spoofing detection method. And anyway, so if you investigate, if you look at this kind of research topics, you need to understand the inside of the GNSS, inside of the GNSS receivers. So for that purpose, so software GNSS receivers will be very useful tool for students as well as young researchers. Yeah, finally, so this is alternate radio navigations. As I already mentioned about LEO, so maybe in the near future, we have a lot of LEO. And if we know the specifications of LEO, it's like center frequency and what kind of Doppler frequency we have. If we know, so we can use this fingerprint-like positioning using only Doppler frequency of LEO. And firstly, received Doppler frequency is determined by the positions. This is true. Yeah, we can simulate this one. And also we prepare a Doppler map according to the grid positions. It's like this, like shown in this figure. And this is the simulation side and the real side. So in reality, so we prepare the receivers and we compare the received Doppler with prepared one in these simulations. We compared. If the received Doppler frequency match with the prepared one, yeah, we can choose the grid. For example, this is the case of the just one case. Received Doppler frequency is 3,456.32 Hertz, and the nearest position grid is here. It's here, 3,456.3. And if we use LEO like Iridium, yeah, this is just an example. Yeah, the each beam is actually it's about 30 meters to 60 meters in beam. Yeah, which means if we know the Doppler frequency of LEO, we can choose the grid, and the accuracy of the position is about within 100 meters. 100 meters. Yeah, as I already mentioned about the spoofing issues, so even in the case that we cannot use GNSS in the very difficult situations like spoofing attack, so we can use this Doppler frequency based positions. Yeah, this is just one example of alternate radio navigation, but probably comparable to the GNSS improvement. Other radio navigation, robust radio navigation will be still important for the users. Okay, so this is the end of my introduction of our laboratory. So we actually working on research topics other than those listed above. And we accept international students and researchers from overseas. If you are interested in our laboratory research topics, and also if you have any questions, please email me. Thank you very much.